Before the Earth, Moon, Sun, stars, and the galaxies formed, the universe was a primordial soup, a dense fog of hot plasma and violent energy. Within the first milliseconds after the Big Bang, 13.7 billion years ago, all the stuff that makes up the entire universe was formed. But how? It is a mystery that researchers are eager to understand. To study it, they are actually creating mini Big Bangs in the laboratory. The experiment is set to run in the world's largest atomic accelerator, LHC at CERN. The project is called ALICE, which stands for a Large Ion Collider Experiment, and it has required completely new super equipment. Part of that equipment is developed by researchers from the Niels Bohr Institute at the University of Copenhagen. For the last 4 years, high-energy nuclear physicists from the Niels Bohr Institute have been designing and building a detector that will resolve some of the mystery about the origin of the universe, the creation of matter, and the fundamental forces of physics.
This is particularly what we call the strong nuclear force, which is the force that binds quarks and gluons together inside the tiniest parts of matter. And we know quite a bit of the strong nuclear force, but we don't know what happens if we have very high temperatures, very high pressures. We think there will be like a soup of quarks and gluons as we expected it to be in the very early universe.
To explore the Big Bang, researchers will create mini Big Bangs. And to record what happens, they have developed an advanced detector. The detector will be unimaginably sensitive. It must measure the particles that are created when atomic nuclei in the mini Big Bangs crash into each other with such colossal energy that they are dissolved into billions of infinitesimally tiny particles. The sensors in the detectors are hand-sized segments mounted on semicircle plates.
Yes, it's a thin disc made out of silicon, a semiconductor material, very pure stuff, the same you use to make electronic chips out of. Here we've got a big electronic chip where we'll be able to measure the particles that go through. A lot of particles go through, we can measure every one of them where they pass.
The detector is extremely fragile, and the two electronics technicians, Bjorn Rasmussen and Jimmy Cayley Hansen, work very carefully and precisely. They wear lint-free suits, and they must never touch the surfaces of the segments, which are the very sensors. So how does one avoid touching them? They come up with a creative solution: to use a toy suction cup. The finished detector will be installed in the huge particle accelerator, the LHC at CERN, the European Organization for Nuclear Research near Geneva.
These silicon discs we have mounted in half ring and then in full rings around a vacuum pipe, a pipe that goes 27 kilometers around under the Earth.
Beams of lead nuclei will be sent into the 27-kilometer-long particle accelerator in opposite directions. They are accelerated to reach almost the speed of light and then smashed together in a head-on collision. In the violent collision, the temperature raises to 100,000 times higher than the Sun's inner core, and for a fleeting instant, the lead nuclei melt to a quark-gluon plasma, similar to the state the universe presumably existed in just after the Big Bang. In the melted state, the nuclei are dissolved and the fundamental particles stream away from the crash point. It is these particles that the researchers will explore with the Danish detector. The particles will hit the extremely sensitive detector, and as many as 80,000 particles may pass through per second. But the particles not only have to pass through the detector's silicon segments, they also have to be recorded.
On the surface of the silicon, we have aluminium strips, which are meant for the electronic readout of the signal. So in fact, there are 512 strips along here on the two halves. And the idea is that and then there's a normal aluminium backside on here. On the front here, we would put an electronic board specially made to fit with our electronics amplifiers on the top. And then we can make small wire bonds all along the side here, 512 on each side, to connect these aluminium strips up to the electronics.
Amplifiers have to be attached to every single aluminium strip, so every particle that passes through is recorded. The green cables must be connected to the electronics boards on the back side. That was one. This is pioneering research. No one has ever built such equipment before. Every bit is thought out, designed and built from the bottom. Many problems arise along the way, and step by step they must find a solution. Electronics technician Bjorn Rasmussen checks that all the cables are properly attached. Electronics technician Thomas Dura solders the chip connections. The first connection I'm making here pushes the chip down, so it gets attached to the circuit board. A single chip is only 2 to 3 centimeters and has more than 100 connections, which are so close together that he has to work with a microscope. Usually you have no idea if you've got it connected, so you have to check afterwards with a really strong magnifying glass and make your own inspection. It's perfect. In the electronics laboratory, the two physicists, Christian Holm Christensen and Christian Gulbrandsen, work on the electronics that will register all the particles that hit the silicon sensors. They've developed the computer software that controls the electronics, which in turn controls the sensors. This is the equipment that's going to forward the signals to a large computer when the sensors have been hit by particles. The sensors may detect up to 80,000 particles per second. The ultra-sensitive detector must record the location of each of the striking particles. The data are sent by the electronics to a huge computer grid, specially designed to process the enormous amounts of data. A new part of the detector is ready for assembly. In all, the detector is made of 10 semicircles that are going to be attached in 5 rings. Finally, they are put together in 3 parts: a cone with 2 rings, a cylinder with 2 rings, and a disc with 1 ring. After nearly 2 years, just for the building phase, the sections are packed into a specially built crate and transported to CERN for installation in the huge atomic accelerator. Here, the Danish detector will be a part of the large international project to solve some of the mysteries of the universe.